Hello, my name is Vladimir Mankov, and together with my colleagues Vladimir Diart and Irina Krasnova, I present a paper, an extensible network traffic classifier based on machine learning methods. The main idea that inspired us for this topic is the development of dynamic real-time quality of service approach based on machine learning methods and new capabilities for collecting statistics in the SDN environment. Despite the source of our inspiration, the results of the analysis of the mechanism discussed in our work can be applied to any network and not only to SDN networks. By the time we moved to the machine learning classification block, we assume that our model has collected general real-time statistics on the flow and individual statistics on packet. This imposes certain features on the nature of statistical data, which we will use when constructing the feature matrix. The methods and new features of collecting real-time statistics using P4 language in SDN environment are described in more details in our previous works. To show the next purpose of our work, we place on this slide the third block, traffic engineering, which will be based on classification results. This is not the focus of our current work, but the goal leaves its mark on the nature of our research. Decision tree is a logical structure which consists of leaves and nodes. They determine whether a feature of a selection element matches a condition occurs in the nodes. The determination if the element belongs to some of the classes performed in leaves. The algorithm itself is unstable and rarely used in production, but it is basic for ensemble models such as a random forest, XGBoost, and extremely randomized trees. Random forest and extremely randomized trees are a set of decision trees that are built in parallel and independently of each other, and the results of predictions is decided by a majority vote. The randomness factor has a more significant impact when constructing extremely randomized trees, comparing to random forests. XGBoost uses multiple decision trees built sequentially, one after the other, and correcting each other's errors. Agglomerative is a hierarchical clustering model based on the bottom-up approach. Each sample element is initially represented as its own separate class, and as the distance between objects increases, the sample elements are combined into clusters. Thus, unlike most other clustering methods, agglomerative allows us to control the number of clusters depending on the distance and determine the clusters closest to the sample. Some standard approaches like Euclidean distance, Manhattan, Mahalanobis, and any other distance matrices can be selected as distances. Our traffic classification model works in real time and can detect and add new classes to its database. The initial training of the model is carried out on pre-marked flows, so they have both training and test sequences, which means that it is possible to correct the behavior of the algorithm in all parts of the scheme, build on all the necessary decision trees, and determine the initial clusters. This research focuses on adding new flows to the model. The flow is identified for each packet in the network based on 5 tuple: IP source, IP destination, port source and destination, and protocol field. The switch records the arrival time of each packet and its size for the first 15 packets of the single flow. This data is then sent to the controller. The controller calculates the feature matrix, which consists of inter-arrival time, packet length, and their average characteristics. The generated feature matrix is used to automatically classify flows using the supervised learning methods, a random forest and XGBoost. Appropriate traffic engineering policies are applied to the classified flow. At the same time, information about the incoming packet comes from the feature matrix to the database, which contains information about all flows that have passed through the network. After n flows pass through the network, the classification model is automatically updated. Extremely randomized trees are built based on the existing database. This tree is used to calculate the distance matrix between samples, normalized in the range from 0 to 1. Using a pre-calculated distance matrix allows following a uniform approach for determining distances and classifying traffics, since both use decision tree algorithms. Also, this helps to fix the position of known samples, since clustering algorithms do not provide for marked sequences. The clustering unit receives information about the distances between samples and performs clustering. For this block, the model uses the agglomerative clustering. The clustering is based on the minimum distance between clusters. It is important to note that the number of classes should not decrease with each new clustering procedure. This decrease of clusters number may occur when adding one that occupies an intermediate position between some of the existing clusters to the database. Thus, the distance between them becomes smaller than the one selected initially, and several clusters are combined into one. The labels of existing samples are fixed to prevent this problem, and in controversial situation, the distance selected for clustering is reduced. The sample placed in the clustering block becomes the base for training the random forest and XGBoost algorithms. Thus, the location of clusters and the distance between them are clarified. New classes are introduced, allowing the model to remain constantly up to date in real time. The experimental research used 15 minutes traffic traces collected in January-February 2020 by the MAWI research group as a part of the WIDE project on a real network section. The initial data markup was performed using the NDPI tool. 1,500 flows of the most common TCP applications were selected for the first experiment, and the first clusters were created based on them. These include DNS, Apple, IMAPS, HTTP, SSH, and Telnet. The T-distributed stochastic neighbor embedding visualization method, which is widely used in machine learning, allows to lower the dimension of data and draw it in two-dimensional space so that points from one sample are most likely to be closer to each other, and points from different samples are more likely to be further away from each other. The method is highly dependent on random components and doesn't accurately determine the distance between points, but it can assist in getting an idea of clustering possibility and the data set. The selected TCP applications were visualized using the TSNE method. Circles mark the trained sequence selections, and crosses mark the test selection. The slide shows that the sample can be divided into clusters, although it has intersections in some places. For example, the intersection of IMAPS, HTTP, and Apple. The appearance of such contested zones can be caused not only by clustering difficulties, but also by protocol features, as well as possible errors in automatic markup. The slide shows the relationship plot between the number of clusters and the minimum normalized distance between clusters, and present the result of clustering depending on the number of resulting clusters. The graph shows that the smaller the minimum allowable distance between the clusters, the more clusters are formed. Note that the number of clusters decreases unevenly despite a uniform increase in distance. Adjusted red index and adjusted mutual information measure the similarity of two assignments, true and predicted, ignore permutations, and normalize all values within the range from -1 to 1, where -1 is bad labeling, 0 is random labeling, and 1 is the best match score. The ARI based on peer counting, and the AMI based on Shannon information theory. The ARI and AMI results show positive close to 0.8, 0.9 for the number of clusters of 12 or more. Homogeneity shows that each cluster contains objects that belongs to only one class. Completeness allows determining the percentage of a single class sample that belongs to a single cluster. V measure is harmonic mean between completeness and homogeneity. All three characteristics are normalized within 0 to 1, where 1 corresponds to the best result. As the number of clusters increases, the homogeneity increases, because with the large number of clusters, some of them may contain quite a small number of samples. In contrast to homogeneity, completeness decreases as the number of clusters increases, because now samples of the same classes belong to different clusters. From the point of view of traffic classification, this is not always an error, since different traffic behavior may correspond to the same application, as shown in the figure of slide 6. Therefore, for the initial operation of the algorithm, you need to select the number of clusters greater than the number of applications in the database. Based on the result of the experiment, 12 clusters, 1 DNS, 1 Telnet, 2 Apple, 2 IMAPs, 2 SSH, and 4 HTTP, with a minimum relative distance between clusters of 0.9997 were selected for the initial training of the model. 300 flows from each of the RTMP, IMAP, SMTP, and Skype applications were added to the model input in turn to test the model ability to detect new types of classes. The number of clusters was measured after each addition, and the nearest neighbors to the new clusters were identified. The figure shows a graph of how the number of clusters formed depends on the composition of application. You can see that each time a new class is added, a new cluster is added, except in case of IMAP. This is due to the presence of a small HTTP clusters that is combined with the IMAP samples. Two different nearest neighbors were determined for the new applications. This information can be used for the traffic engineering policies. To evaluate the capabilities of working in real time, we measured the model construction time and the simultaneous classification time for various numbers flows. The result will also help to determine the number of the new flows, n, after which the model needs to be updated. The figure shows the average construction and operation time of the model's individual components. Agglomerative clustering model building time significantly exceeds the building time and the running time of the classifiers. This explains the advantage of the random forest and XGBoost methods for the real-time classification. Accuracy of the random forest and XGBoost classification according to the given database reaches values of 0.99 till 1. XGBoost can achieve better results on large samples compared to random forests and high speed of the model, regardless of the number of simultaneously classified flow. However, it takes longer to build the model than in case of random forest usage. Consider these circumstances when choosing a classification tool. Our research offers an experimentally tested approach to solving the problem of traffic classification using machine learning methods, which has the following advantages. First of all, the ability to work in real time due to high-performance network monitoring, a new method of feature matrix formation, and fast model operation time, just 2 milliseconds, using supervised learning method. Second, the ability to detect new flows that are unknown to the model using unsupervised learning algorithms. Third, identifying the nearest classes as auxiliary information for traffic engineering. In addition, the model automatically updates itself, taking into account the current situation in the network. The model doesn't require a large initial database because the algorithm can be trained in the process. The model provides high classification accuracy, up to 90% for all indicators. It has a flexible classification granularity due to changes in the distance between clusters and, as a result, the number of clusters. Also, it adjusts the refresh rate of the model depending on the network activity. The main disadvantage of this method is that it reduces accuracy during the new flows classification, since the model is updated after they are classified. This assumption was made in the model consciously. Direct clustering would take too much time and cause significant delays. Besides, there are no traffic engineering policies for unknown classes in the network. So, even with the fast clustering, further application of its result would be impossible. And for a small rare number of flows, it is pointless. Our proposal allows to coordinate the introduction of new classes with traffic engineering policies at the time of updating model. And when new classes appear, use rules that work for traffic flows with similar statistical characteristics. We plan to apply our method of intelligent traffic classification for adaptive routing purposes in our future works.